Hey, hope you're still doing well. In this video, what we're going to do is we're going to talk about the properties of logarithms. There's really only, well, there's kind of five of them, but we group one of them together, so it's really only four. We're going to talk about the four properties of logarithms, just some basic examples on how they work, and then we're going to use those in the next few videos to combine some logarithms, expand some logarithms, use what's called the change of base formula, and then we'll be finally ready to start tackling some of these problems that have some complicated equations with exponentials and logarithms. Just understanding these ideas. So here are the properties of logarithms as you need to know them. The first one is this. I've said a couple of these before, but there's some things that we need to remember all the time. Number one, if you ever have a logarithm where the argument is 1, you're going to get 0. And here's the reason why. Any base raised to the 0 power is always going to give you 1. Therefore, a logarithm of any base of 1 is equal to 0. This is exactly where, man, I hope you remember it. When we graph logarithms, this is exactly where the key point of 1, 0 comes from. Input of 1, output of 0. 1, 0 is on every single logarithm before you start shifting it. That's where that came from. Likewise, a logarithm with a base of a, if you have the same base here and here, this is always going to equal 1. Why? Because a to the first power is always going to give you a. Actually, to the first power. It's almost a trivial statement. It says a raised to what power gives you a? A to the first power gives you a. And is consequently why on every graph of a logarithm, you had a key point of a1. You plug in a, you get out 1 for whatever base you have. I hope that makes sense to you. We had 1, 0. We had a, 1 for every logarithm ever. That's where they come from. And that's why these properties work, is if you have a 1, you're going to get a 0. If you have an a, you're going to get a 1. And that translates to one more thing. This is extendable. So a to the first power gives you a to the first, but a to the r power is going to give you a to the r. Look at what we have done. We've talked about in the last video, but we've composed an exponential onto a logarithm with the same base. Two inverses, an exponential and a logarithm, are always going to cancel each other out. So when you compose them in either order, everything's going to go away. Everything's going to cancel out. And you get these trivial statements. You say a raised to what power is going to give you a to the r power? Well, this would have to be r. And if you think back to what happened when we composed a function and its inverse, everything canceled and you got x. Well, in this case, our x is actually r. So everything's going to cancel. You're going to get r. And that's exactly what's happening here. You have an exponential on a logarithm, the same base, they're going to cancel and give you whatever that exponent is. In this case, you're going to get r. And it says the same thing, a to the r power equals a to the r power. We've explored this before. What we haven't seen is this one. It is a similar concept. You just compose the inverses differently. Now, we know from compositions, whether we compose a function and its inverse or an inverse and its function, you still get the same thing. You still get everything cancels out. Same thing happens here. When you compose a logarithm onto an exponential, this acts as the exponent of some exponential, but it has the same base. So you've composed a function on its inverse. It will cancel and give you, in this case, m. And what it says is, if you were to go and write this in logarithmic form right now, it's in exponential form, it would say, you'd have a log, let's see, I'm going to do this for you. You'd have if I would do logarithms, here's my base. I have to do it over here, because I didn't plan on doing this. Here's my base of a, here's my exponent. A logarithm takes the base and separates the exponent. Here's my base as a logarithm, here's my exponent, and makes the argument whatever this is. And we get a trivial statement. And this is saying the same thing as that. It's saying, hey, what would my argument be if I have log base a of something equals log base a of m? It would have to be m. That's what that's saying. So how we use these is really nice. These are extremely quick. Just understand the nature of what you're doing. Don't treat it like just a rule. Don't be like, oh, it's -13, 1/3, -4, 7, 1/4, and 8. Those are all true. But think about what is happening. You have composed an exponential with a base of 2 on a logarithm base of 2. Those are two inverse functions composed. When you compose inverse functions, they cancel. You're going to get negative 13, and that's why. Now, it is just this rule, isn't it? Here's our base is the same. We're just going to get the exponent, and that's what's going on. But the reason behind it's important to know. Next one, hey, have you composed a logarithm and its inverse? Well, an exponential and its inverse of a logarithm. That's a base of 10. That's a log with a base of 10. We don't write it, but that's a base of 10. So you have an exponential on a logarithm with the same base. It's going to cancel. You still have this property right here with the same bases. They're going to simplify, and you're going to get 1/3. Same thing happens here. We have an exponential with a base of e. We have a logarithm with a base of e. Now we write that as ln, but that is a log base e. An exponential composed on a logarithm, the same bases. Your bases match up. You're going to simplify. This is going to give you -4. All of these things should make sense to you. 2 to the -13th power equals 2 to the -13th. 10 to the 1/3 power equals 10 to the 1/3 power. They're trivial statements. Why? Because you've composed a function on its inverse. E to the -4th power equals e to the -4th power. Yep. How about this one? Well, this is the other way. We've composed a logarithm onto an exponential, but you still have the same base. This is a function composed on its inverse. It's going to simplify and give you, in this case, 7. We're right here right now. Bases match up. They're going to simplify. Same thing happens here. Log base 10 on an exponential base 10. Well, you've composed a function on its inverse. That has to simplify, has to cancel out. Here you have a log base e on an exponential base e. You've composed a function on its inverse. Those have to cancel out. And these are all 3 instances of this property. Where you have the bases the same, you're going to simplify and get just the argument every time. That's pretty useful. We see that from time to time. We're going to see it in a couple of these examples where we have composed a function on its inverse. Either purposefully, that's when we're solving. We're purposely composing a function on its inverse when we're solving exponentials and logarithms. Or in the working out or simplification of some of our logarithms, we sometimes see this and then we can simplify as we go. That's very useful. Let's go on to the next couple properties. So the next ones, in order to really make these stick, I want you to think about how logarithms are created. Logarithms come from some sort of an exponential. They're an inverse of an exponential. And because of that, these properties mimic exponential rules. So think exponent rules. Now they're not exactly exponent rules because they're not exactly exponents. They come from exponentials, but they're not exponents themselves. And so they model those exponent rules pretty closely, but they're not exact. So well, they're inverses. So check it out. If we ever have log base a of a product, so m times n, we can separate that. We can separate that by using addition. Now why addition? Well, when you multiply common bases, don't you add those exponents? Well, yeah. So multiplication is somehow tied together with this addition concept, much like you have for exponents. And that's a true statement for logarithms. If you have a product inside of one logarithm, you can separate this into 2 logarithms with the same base of a sum. So a sum of 2 logarithms. Also, this is a really big note. I want you to make a really important note here. This is not a one-way street. So what that means is, if you have 2 logarithms and they're added together and they have the same base, you can multiply their arguments inside one logarithm, not add. Notice what is not up here. Nowhere have I had logarithm of base a of m plus n. That's not expandable. And nowhere will I have log base a of m times log base a of n. That's not combinable. That doesn't work. And so what I'm giving you here, this is really important, is that I'm giving you the only rules that actually work to expand and combine logarithms. Don't think outside the box here. Don't invent your own math. It's really common for students to do, but we just cannot do it. If it's not up here, then you can't do it with logarithms. If I haven't told it to you, and the only other one that I can think of is change of base right now. We're going to get that a little bit later. But if it's not one of these, you can't expand by it, you can't combine by it. So the next one's very, very similar. Imagine this. Imagine if you're multiplying and multiplication gives you some sort of addition concept, what's division going to give you? Multiplication is to division as addition is to subtraction in the case of our logarithm rules. So what we do here, if we have a log base a of m divided by n, we can separate that, we can expand it by subtraction. Think of your division of exponents. If you had x to the m over x to the n, we would subtract those exponents, and that's sort of where this is coming from. So if we have log base a of m divided by n, division is somehow tied together with the subtraction concept. Also, these are not one-way streets, they're two-way streets. So you can expand a logarithm with division inside as subtracting a difference of two logarithms of the same base. Or if you have two logarithms of the same base being subtracted, you can combine it into a logarithm with division, not subtraction. These are both important. We use both of these when we're solving exponentials and logarithms. We need to know them kind of backwards and forwards to be able to expand and combine. All right, the last one's called the power property. If you ever have an exponent, log base a of something to some exponent, you can move that exponent or power, called the power property, to the front as a coefficient. Fascinating piece of math, but what it says is that you can expand any sort of exponent as a coefficient, or if you have a coefficient, you can move that as an exponent. This is how we start isolating logarithms to make it one logarithm without anything multiplied or divided. We can move that as an exponent. Well, likewise, if you have an exponent, you really don't want it. Like, what if that's a radical? Wait a minute, a radical is like a 1/3 power, or 1/2 power, or a fractional exponent. You can now move that as a coefficient. You can get rid of any radicals inside of your logarithm, provided the entire argument is under that radical. Well, that's really neat, and that really helps us out in a lot of cases. So we can go backwards and forwards with that power property. Now it's time to practice it. Let's take these. I'm going to show you the thought processes going through. We'll expand all of these and just use some of the properties that we can as we go through. So when we start talking about log base 5 of 25 to the x, and we're trying to simplify this, here's some things that we can think of. Number one, can you expand via products? Can you understand that if that's a product, I can expand this? Well, how would I do it? If I look back, there's only one thing that lets me expand a product. It says I can take log base 5 of 25 plus log base 5 of x. The only reason I have the parentheses here is to make sure that we understand this is the end of the argument. I'm not adding something inside of that logarithm. So log base 5 of 25 plus log base 5 of x says product equals plus. That's what I need in your head. Product equals plus, plus equals product. Can we simplify further? Well, log base 5 of x, that's not simplifiable. There's nothing, we don't know what the x is, so there's nothing we can really do. But log base 5 of 25, there are a few ways to simplify this. Now, this is going to lead us down to the statement that there's more than one way to do a lot of this work with logarithms. As long as you're using an appropriate property that we've seen, you're going to be fine. I'm going to show you at least two ways to think about this. Here's the first way to think about this. First way is, I'll show you three ways. The first way is, can you just think 5 raised to what power gives you 25? And you go, 5 squared is 25. Oh, hey, 2. This is going to be 2, guaranteed. That's one way you could do it. Another way you could do it. Could you write this as log base 5 of 5 squared? Well, sure, 25 is 5 squared, but think about what this means. If this is base, and they're the same, you now have this property. Log base a of a to the r is log base 5 of 5 to the second. The log base 5 and the 5, that's an exponential composed on a logarithm with the same base. That's inverses composed. They're going to cancel. You're going to get 2. What else could you do? Could you now use this property and move your exponent to the front? Well, that's possible. Here's my exponent. I can move it to the front as a coefficient. Log base 5 of 5 to the first power, or simply log base 5 of 5. That's this property. That's going to give you 1. Oh, wait. Hey, do you remember that on every single logarithm we have the base comma 1? That's what that's saying. That says log base 5 of 5. Let's see, how to get to 5? From 5 to 5. What power is that? That's a power 1. So this would simplify to a 1. 2 times 1 is 2. No matter what, you're going to end up getting 2 plus log base 5 of x. Now that is as simple as we can make it, but understand what this does for you. This makes something a lot easier to graph. That might be kind of difficult to graph. This is not. Oh man, I hope that you see this. This is a logarithm. It's got a base of 5. So that means we have a point 1, 0, and 5, comma 1. Those are my key points. Furthermore, that's a shift up 2 units. There's no horizontal shift, but this is out of order. That's a shift up 2. Got a key point of 1, 0, got a key point of 5, 1. There's no horizontal shift at all. There's no vertical stretch. You could graph this very easily with what I've taught you in the graphing video. I hope that's fascinating, that doing this makes it easier to actually do things like graphing. Cool. We're just using some very simple properties. Okay, let's focus on the next one. So we've got this ln of e over x. The first thing I want you to notice is that we can separate quotients if we're talking about expanding by subtraction. So when we do that, that says take your logarithm, that is a logarithm, it has a base of e, and take that quotient, create 2 logarithms that are being subtracted. So division creates a subtraction concept for us. And then we see if we can simplify each one. ln x, well, there's nothing we can really do, much like the log base 5 of x in the previous example. But ln e, well, wait a minute. This has a base of e. This is exponential with a base of e. You've just composed an exponential onto a logarithm with the same base. They're going to cancel, but they're not going to give you 0. This is this case right now. So we have the same base. Even though we don't write log, we write ln, it still is a base of e and a base of e. They're going to simplify and they're going to give you 1. If you want to think down this route, if you want to write the base of, the exponent of 1 there, base matches base, exponential composed on logarithm with the same base, it's going to cancel, it's going to give you 1. That's about as good as we can make it, but notice that you could graph this a bit easier. Oh man, do you see it? Do you see that this is a logarithm of the base of e. So what are your key points? Well, your key points are 1, 0, and e, comma 1. It's like 2.7, comma 1. This is shifted up 1 unit. This is then reflected. You'd affect the outputs of your key points. It would reflect that exponential. I hope I'm making it make sense to you. I hope I'm making you see the connections of what I've taught you to what you're doing now. It should not be completely separated. It should be one big unit of information. It's like, oh, this relates. This is now easier to graph than that. Do you want to graph that? I don't want to graph that. Do you want to graph that? That's easy. That's a shift up 1. That's a reflection. I've got key points of 1, 0, e, comma 1. My outputs would reflect, and I could graph it very nicely. That's much nicer. Okay, last example. It starts out pretty much the same. We've got this logarithm of this division. So this quotient inside of one logarithm, we can expand it, and sometimes it's very nice we're seeing this. This is much easier to graph if we expand that. So let's do it. So this logarithm would be ln of the numerator minus the denominator. I probably would put parentheses here. I might put parentheses here. You don't have to. There's nothing after it. But we do need to understand how this works. How this works is it takes and makes the first logarithm of your numerator minus the logarithm of your denominator. That order is important. It's not commutative. You can't switch it around. So numerator is first, denominator is second in that difference. After that, we look to simplify whatever we can. ln x, you're done. There's really nothing we can do there. There's no bases that match. There's no moving exponents. There really isn't an exponent besides 1, and that doesn't help us to move. You just get 1 times something, which gives you back that something. It's multiplicative identity. So that doesn't really affect anything. But ln of e to the x, I need you to notice that. I need you to notice that we are here. I'm gonna throw a lot of these at you so that you do recognize It's very common in calculus for students to not simplify that because they're not seeing that e explicitly. Ln of e to some exponent is always cancelable because you've composed an exponential on a logarithm of the same base. So you can see why I'm throwing these at you so that you go, oh yeah, that's right. Okay, that simplifies. So that I'm getting you in the mode of when you see this later, you can understand why they're calling this just x. It's not magic, it's composing an exponential on a logarithm going, oh, that is certainly going to simplify. We actually have a property for that. This says e to what power gives you e to the x? Well, e to the x gives you e to the x. You're going to cancel this. It is an exponential composed on the inverse of a logarithm. It's going to simplify to just x. Just like this simplifies just to 1/3. Your bases match. I just need you to see it. You compose a function with its inverse and that cancels. So that's where we're going to end here. This is a little bit more difficult to graph than some of the other ones, but it is possible. It's certainly easier than trying to graph that thing. So I hope that I've explained these properties to you, that they're loosely based on exponent rules, which is why products are mapped to pluses and quotients are mapped to differences. This one's a little special with what we can do with the exponent. We get into that a little bit later on why that actually works. So watch out for that. We'll come back with how to combine and expand logarithms in general. So we'll deal with expanding first as much as we can, much harder than what I've given you here. This is just an introduction, and then we'll talk about how to combine them. And then we'll be ready to solve exponentials and logarithms in general. Hope you're having fun. Hope you're doing well. See you soon.